Welcome to this machine learning tutorial. To work on the examples, you'll need Jupyter Notebook. We are using a Docker image that comes with all packages pre-installed. In the info card and description of the video, there is a step-by-step tutorial on how to set up an environment like the one in this tutorial. Scikit-Learn. There are several Python libraries which provide solid implementations of a range of machine learning algorithms. For this tutorial, we will use Scikit-Learn, one of the best known. So if you are getting into the data science field, then this library is going to be essential to learn because it provides efficient versions of a large number of common algorithms. Model selection. In principle, model selection is very simple. After choosing a model and its hyperparameters, we can estimate how effective it is by applying it to some of the training data and comparing the prediction to the known value. Let's demonstrate the naive approach to selection using the IRIS dataset, which famously analyzed by Ronald Fisher in 1936. We will start by loading the data. Next we choose a model and hyperparameters. Here we'll use a k-neighbors classifier with n neighbors equals 1. This is a very simple and intuitive model that says the label of an unknown point is the same as the label of its closest training point. Now let's hold back some subset of the data from the training of the model and then use this holdout set to check the model performance. This splitting can be done using the train test split utility in Scikit-Learn. The nearest neighbor classifier is about 90% accurate on this holdout set. The holdout set is similar to unknown data because the model has not seen it before. Model validation via cross-validation. Cross-validation is to do a sequence of fits where each subset of the data is used both as a training set and as a validation set. Here we do two validation trials, alternately using each half of the data as a holdout set. Using the split data from before, we could implement it like this. What comes out are two accuracy scores, which we could combine by, say, taking the mean, to get a better measure of the global model performance. Here we split the data into 5 groups and used each to evaluate the model fit on the other 4/5 of the data. For example, we might wish to go to the extreme case in which our number of folds is equal to the number of data points. That is, we train on all points, but one in each trial. This cross-validation type is called leave one out cross-validation and can be used as follows. Because we have 150 samples, the leave one out cross-validation yields scores for 150 trials, and the score indicates either a successful 1.0 or unsuccessful 0.0 prediction. Taking the mean of these gives an estimate of the error rate. Selecting the best model. Now that we've seen the basics of validation and cross-validation, we will go into a little more depth regarding model selection and the selection of hyperparameters. Validation curves in Scikit-Learn. Let's look at an example of using cross-validation to compute the validation curve for a class of models. Now let's create some data to which we will fit our model. We can now visualize our data, along with polynomial fits of several degrees. We can progress in this by visualizing the validation curve for this particular data and model. This can be done straightforwardly using the validation curve convenience routine provided by Scikit-Learn. This shows precisely the qualitative behavior we expect. The training score is everywhere higher than the validation score. The training score is monotonically improving with increased model complexity, and the validation score reaches a maximum before dropping off as the model becomes overfit. From the validation curve, we can read off that the optimal trade-off between bias and variance is found for a third-order polynomial. We can compute and display this fit over the original data as follows. Notice that finding this optimal model did not actually require us to compute the training score, but examining the relationship between the training score and validation score can give us useful insight into the performance of the model. Learning curves. One important aspect of model complexity is that the optimal model will generally depend on the size of your training data. For example, let's generate a new dataset with a factor of 5 more points. We will duplicate the preceding code to plot the validation curve for this larger dataset. For reference, let's overplot the previous results. The solid lines show the new results while the fainter dashed lines show the results of the previous smaller dataset. Learning curves in Scikit-Learn. Scikit-Learn offers a convenient utility for computing such learning curves from your models. Here, we will compute a learning curve for our original dataset with a second-order polynomial model and a ninth-order polynomial. This is a valuable diagnostic because it gives us a visual depiction of how our model responds to increasing training data. Validation in practice. Grid search. Here is an example of using grid search to find the optimal polynomial model. We will explore a three-dimensional grid of model features, namely the polynomial degree, the flag telling us whether to fit the intercept, and the flag telling us whether to normalize the problem. This can be set up using Scikit-Learn's grid search meta estimator. Notice that, like a normal estimator, this has not yet been applied to any data. Calling the fit method will fit the model at each grid point, keeping track of the scores along the way. Now that this is fit, we can ask for the best parameters as follows. Finally, if we wish, we can use the best model and show the fit to our data using code from before. The Hyperparameters and Model Validation chapter we outline the fundamental ideas of machine learning, but all of the examples assume that you have numerical data in a tidy format. In the real world, data rarely comes in such a form. With this in mind, one of the more important steps in using machine learning in practice is feature engineering. That is, taking whatever information you have about your problem and turning it into numbers that you can use to build your feature matrix. Categorical features. One common type of non-numerical data is categorical data. For example, imagine you are exploring some data on housing prices, and along with numerical features like price and rooms, you also have neighborhood information. For example, your data might look something like this. In this case, one proven technique is to use one-hot encoding, which effectively creates extra columns, indicating the presence or absence of a category with a value of 1 or 0, respectively. When your data comes as a list of dictionaries, Scikit-Learn's dict vectorizer will do this for you. Notice that the neighborhood column has been expanded into 3 separate columns, representing the 3 neighborhood labels, and that each row has a 1 in the column associated with its neighborhood. With these categorical features thus encoded, you can proceed as normal with fitting a Scikit-Learn model. To see the meaning of each column, you can inspect the feature names. There is one clear disadvantage of this approach. If your category has many possible values, this can greatly increase the size of your dataset. However, because the encoded data contains mostly zeros, a sparse output can be a very efficient solution. Text features. Another common need in feature engineering is to convert text to a set of representative numerical values. For example, most automatic mining of social media data relies on some form of encoding the text as numbers. One of the simplest methods of encoding data is by word counts. You take each snippet of text, count the occurrences of each word within it, and put the results in a table. For example, consider the following set of 3 phrases. For a vectorization of this data based on word count, we could construct a column representing the word problem, the word evil, the word horizon, and so on. While doing this by hand would be possible, the tedium can be avoided by using Scikit-Learn's count vectorizer. The result is a sparse matrix recording the number of times each word appears. It is easier to inspect if we convert this to a data frame with labeled columns. There are some issues with this approach, however. The raw word counts lead to features which put too much weight on words that appear very frequently, and this can be suboptimal in some classification algorithms. The syntax for computing these features is similar to the previous example. Derived features. Another useful type of feature is one that is mathematically derived from some input features. For example, this data clearly cannot be well described by a straight line. Still, we can fit a line to the data using linear regression and get the optimal result. It's clear that we need a more sophisticated model to describe the relationship between x and y. One approach to this is to transform the data, adding extra columns of features to drive more flexibility in the model. For example, we can add polynomial features to the data this way. The derived feature matrix has one column representing x, and a second column representing x2, and a third column representing x3. Computing a linear regression on this expanded input gives a much closer fit to our data. This idea of improving a model not by changing the model, but by transforming the inputs, is fundamental to many of the more powerful machine learning methods. Imputation of missing data. Another common need in feature engineering is handling of missing data. For example, we might have a dataset that looks like this. When applying a typical machine learning model to such data, we will need to first replace such missing data with some appropriate fill value. This is known as imputation of missing values, and strategies range from simple, e.g., replacing missing values with the mean of the column, to sophisticated, e.g., using matrix completion or a robust model to handle such data. The sophisticated approaches tend to be very application-specific, and we won't dive into them here. For a baseline imputation approach using the mean, median, or most frequent value, Scikit-Learn provides the imputer class. We see that in the resulting data, the two missing values have been replaced with the mean of the remaining values in the column. This imputed data can then be fed directly into, for example, a linear regression estimator. Feature pipelines. With any of the preceding examples, it can quickly become tedious to do the transformations by hand, especially if you wish to string together multiple steps. For example, we might want a processing pipeline that looks something like this. Impute missing values using the mean transform features to quadratic fit, a linear regression. To streamline this type of processing pipeline, Scikit-Learn provides a pipeline object, which can be used as follows. This pipeline looks and acts like a standard Scikit-Learn object and will apply all the specified steps to any input data. All the steps of the model are applied automatically. Notice that for the simplicity of this demonstration, we've applied the model to the data it was trained on. This is why it was able to perfectly predict the result. Please don't forget to find all code in GitHub and Mstarlog link in the description. You will find handy code and all the code used in this video tutorial. Naive Bayes classification. We will be taking a closer look at several specific algorithms for supervised and unsupervised learning, starting here with naive Bayes classification. Bayesian classification. Naive Bayes classifiers are built on Bayesian classification methods. These rely on Bayes' theorem, which is an equation describing the relationship of conditional probabilities of statistical quantities. We begin with the standard imports. Gaussian naive Bayes. Perhaps the easiest naive Bayes classifier to understand is Gaussian naive Bayes. In this classifier, the assumption is that data from each label is drawn from a simple Gaussian distribution. Imagine that you have the following data. One extremely fast way to create a simple model is to assume that the data is described by a Gaussian distribution with no covariance between dimensions. This procedure is implemented in Scikit-Learn sklearn.naivebayes.Gaussian estimator. Now let's generate some new data and predict the label. Now we can plot this new data to get an idea of where the decision boundary is. A nice piece of this Bayesian formalism is that it naturally allows for probabilistic classification, which we can compute using the predict-proba method. The columns give the posterior probabilities of the first and second labels, respectively. Multinomial naive Bayes. Example: classifying text. One place where multinomial naive Bayes is often used is in text classification, where the features are related to word counts or frequencies within the documents to be classified. Let's download the data and take a look at the target names. For simplicity here, we will select just a few of these categories and download the training and testing set. Here is a representative entry from the data. In order to use this data for machine learning, we need to be able to convert the content of each string into a vector of numbers. For this, we will use the TF-IDF vectorizer, discussed in feature engineering, and create a pipeline that attaches it to a multinomial naive Bayes classifier. With this pipeline, we can apply the model to the training data and predict labels for the test data. Now that we have predicted the labels for the test data, we can evaluate them to learn about the performance of the estimator. For example, here is the confusion matrix between the true and predicted labels for the test data. Evidently, even this very simple classifier can successfully separate space talk from computer talk, but it gets confused between talking about religion and talking about Christianity. This is perhaps an expected area of confusion. The very cool thing here is that we now have the tools to determine the category for any string using the predict method of this pipeline. Here's a quick utility function that will return the prediction for a single string. Let's try it out. Remember that this is nothing more sophisticated than a simple probability model for the weighted frequency of each word in the string. Nevertheless, the result is striking. Even a very naive algorithm, when used carefully and trained on a large set of high-dimensional data, can be surprisingly effective. When to use naive Bayes? Naive Bayes classifiers tend to perform especially well in one of the following situations. When the naive assumptions actually match the data, very rare in practice. For very well separated categories, when model complexity is less important. For very high dimensional data, when model complexity is less important. Linear regression. Just as naive Bayes, discussed earlier in naive Bayes classification, is a good starting point for classification tasks. Linear regression models are a good starting point for regression tasks. Such models are popular because they can be fit very quickly and are very interpretable. We begin with the standard imports. Simple linear regression. We will start with the most familiar linear regression, a straight line fit to data. A straight line fit is a model of the form f equals n plus o, where n is commonly known as the slope and o is commonly known as the intercept. Consider the following data, which is scattered about a line with a slope of 2 and an intercept of -5. We can use Scikit-Learn's linear regression estimator to fit this data and construct the best fit line. The slope and intercept of the data are contained in the model's fit parameters, which in Scikit-Learn are always marked by a trailing underscore. Here the relevant parameters are coef and intercept. We see that the results are very close to the inputs, as we might hope. The linear regression estimator is much more capable than this, however, in addition to simple straight line fits, it can also handle multidimensional linear models of the form f equals n0 plus n1 e1 plus n2 e2, where there are multiple e-values. The multidimensional nature of such regressions makes them more difficult to visualize, but we can see one of these fits in action by building some example data using NumPy's matrix multiplication operator. Here the f data is constructed from 3 random e-values, and the linear regression recovers the coefficients used to construct the data. In this way, we can use the single linear regression estimator to fit lines, planes, or hyperplanes to our data. Polynomial basis functions. This polynomial projection is useful enough that it is built into Scikit-Learn using the polynomial features transformer. This new, higher dimensional data representation can then be plugged into a linear regression. As we saw in feature engineering, the cleanest way to accomplish this is to use a pipeline. Let's make a 7th-degree polynomial model in this way. With this transform in place, we can use the linear model to fit much more complicated relationships between E and F. For example, here is a sine wave with noise. Our linear model, through the use of 7th-order polynomial basis functions, can provide an excellent fit to this non-linear data. Gaussian basis functions. Of course, other basic functions are possible. For example, one useful pattern is to fit a model that is not a sum of polynomial bases, but a sum of Gaussian bases. The shaded regions in the plot are the scaled basis functions, and when added together, they reproduce the smooth curve through the data. We put this example here just to make clear that there is nothing magic about polynomial basis functions. Regularization. The introduction of basis functions into our linear regression makes the model much more flexible, but it also can very quickly lead to overfitting. Refer back to hyperparameters and model validation video for a discussion of this. For example, if we choose too many Gaussian basis functions, we end up with results that don't look so good. With the data projected to the 30-dimensional basis, the model has far too much flexibility and goes to extreme values between locations where it is constrained by data. We can see the reason for this if we plot the coefficients of the Gaussian bases with respect to their locations. The lower panel of this figure shows the amplitude of the basis function at each location. Ridge regression to regularization. Perhaps the most common form of regularization is known as ridge regression or to regularization, sometimes also called Tikhonov regularization. This type of penalized model is built into Scikit-Learn with the ridge estimator. Lasso regression, 1 regularization. Another very common type of regularization is known as lasso and involves penalizing the sum of absolute values, 1 norms of regression coefficients. We can see this behavior in duplicating the ridge regression figure, but using 1 lira normalized coefficients. Example, predicting bicycle traffic. As an example, let's take a look at whether we can predict the number of bicycle trips across Seattle's Fremont Bridge based on weather, season, and other factors. We will perform a simple linear regression to relate weather and other information to bicycle counts in order to estimate how a change in any one of these parameters affects the number of riders on a given day. Let's start by loading the 2 datasets, indexing by date. Next, we will compute the total daily bicycle traffic and put this in its own data frame. We saw previously that the patterns of use generally vary from day to day. Let's account for this in our data by adding binary columns that indicate the day of the week. Similarly, we might expect writers to behave differently on holidays. Let's add an indicator of this as well. We also might suspect that the hours of daylight would affect how many people ride. Let's use the standard astronomical calculation to add this information. We can also add the average temperature and total precipitation to the data. In addition to the inches of precipitation, let's add a flag that indicates whether a day is dry, has 0 precipitation. Finally, let's add a counter that increases from day 1 and measures how many years have passed. This will let us measure any observed annual increase or decrease in daily crossings. Now our data is in order, and we can take a look at it. With this in place, we can choose the columns to use and fit a linear regression model to our data. We will set fit_intercept equals false, because the daily flags essentially operate as their own day-specific intercepts. Finally, we can compare the total and predicted bicycle traffic visually. It is evident that we have missed some key features, especially during the summertime. These numbers are difficult to interpret without some measure of their uncertainty. We can compute these uncertainties quickly using bootstrap resamplings of the data. With these errors estimated, let's again look at the results. We first see that there is a relatively stable trend in the weekly baseline. There are many more writers on weekdays than on weekends and holidays. Our model is almost certainly missing some relevant information, for example, nonlinear effects and nonlinear trends within each variable, such as disinclination to write at very cold and very hot temperatures, cannot be accounted for in this model. Support vector machines. Support vector machines, SVMs, are a particularly powerful and flexible class of supervised algorithms for both classification and regression. In this section, we will develop the intuition behind support vector machines and their use in classification problems. We begin with the standard imports. Motivating support vector machines. As part of our discussion of Bayesian classification, we learned a simple model describing the distribution of each underlying class and used these generative models to probabilistically determine labels for new points. As an example of this, consider the simple case of a classification task in which the two classes of points are well separated. A linear discriminative classifier would attempt to draw a straight line separating the two sets of data and thereby create a model for classification for two-dimensional data like that shown here. This is a task we could do by hand, but immediately we see a problem. There is more than one possible dividing line that can perfectly discriminate between the two classes. We can draw them as follows. These are three very different separators which, nevertheless, perfectly discriminate between these samples. Depending on which you choose, a new data point, e.g., the one marked by the X in this plot, will be assigned a different label. Support vector machines, maximizing the margin. Support vector machines offer one way to improve on this. The intuition is this: rather than simply drawing a zero-width line between the classes, we can draw around each line a margin of some width up to the nearest point. Here is an example of how this might look. In support vector machines, the line that maximizes this margin is the one we will choose as the optimal model. Support vector machines are an example of such a maximum margin estimator. Fitting a support vector machine. Let's see the result of an actual fit to this data. We will use Scikit-Learn support vector classifier to train an SVM model on this data. For the time being, we will use a linear kernel and set the C parameter to a very large number. We'll discuss the meaning of these in more depth momentarily. To better visualize what's happening here, let's create a quick convenience function that will plot SVM decision boundaries for us. This is the dividing line that maximizes the margin between the two sets of points. In Scikit-Learn, the identity of these points are stored in the support vector's attribute of the classifier. A key to this classifier's success is that for the fit, only the position of the support vectors matter. Any points further from the margin which are on the correct side do not modify the fit. We can see this, for example, if we plot the model learn from the first 60 points and first 120 points of this dataset. In the left panel, we see the model and the support vectors for 60 training points. In the right panel, we have doubled the number of training points, but the model has not changed. This insensitivity to the exact behavior of distant points is one of the strengths of the SVM model. If you are running this notebook live, you can use Python's interactive widgets to view this feature of the SVM model interactively. Beyond linear boundaries, Kernel SVM. Where SVM becomes extremely powerful is when it is combined with kernels. To motivate the need for kernels, let's look at some data that is not linearly separable. It is clear that no linear discrimination will ever be able to separate this data. For example, one simple projection we could use would be to compute a radial basis function centered on the middle clump. We can visualize this extra data dimension using a three-dimensional plot. If you are running this notebook live, you will be able to use the sliders to rotate the plot. We can see that with this additional dimension, the data becomes trivially linearly separable by drawing a separating plane at, say, r equals 0.7. In Scikit-Learn, we can apply kernelized SVM simply by changing our linear kernel to an RBF, radial basis function, kernel, using the kernel model hyperparameter. Using this kernelized support vector machine, we learn a suitable nonlinear decision boundary. Tuning the SVM, softening margins. Our discussion thus far has centered around very clean datasets, in which a perfect decision boundary exists. But what if your data has some amount of overlap? For example, you may have data like this. To handle this case, the SVM implementation has a bit of a fudge factor, which softens the margin. That is, it allows some of the points to creep into the margin, if that allows a better fit. The plot shown below gives a visual picture of how a changing 6-parameter affects the final fit via the softening of the margin. The optimal value of the 6-parameter will depend on your dataset and should be tuned using cross-validation or a similar procedure. Refer back to Hyperparameters and Model Validation video. Example: face recognition. As an example of support vector machines in action, let's take a look at the facial recognition problem. We will use the labeled faces in the wild dataset, which consists of several thousand collated photos of various public figures. A fetcher for the dataset is built into Scikit-Learn. Let's plot a few of these faces to see what we're working with. Each image contains 62 times 47 or nearly 3000 pixels. We can do this most straightforwardly by packaging the preprocessor and the classifier into a single pipeline. For the sake of testing our classifier output, we will split the data into a training and testing set. Finally, we can use a grid search cross-validation to explore combinations of parameters. Here we will adjust C, which controls the margin hardness, and gamma, which controls the size of the radial basis function kernel, and determine the best model. The optimal values fall toward the middle of our grid. If they fell at the edges, we would want to expand the grid to make sure we have found the true optimum. Now with this cross-validated model, we can predict the labels for the test data, which the model has not yet seen. Let's take a look at a few of the test images along with their predicted values. Out of this small sample, our optimal estimator mislabeled only a single face. Bush's face in the bottom row was mislabeled as Blair. We can get a better sense of our estimator's performance using the classification report, which lists recovery statistics label by label. We might also display the confusion matrix between these classes. This helps us get a sense of which labels are likely to be confused by the estimator. Decision trees and random forests. We'll take a look at motivating another powerful algorithm, a non-parametric algorithm, called random forests. Random forests are an example of an ensemble method, meaning that it relies on aggregating the results of an ensemble of simpler estimators. We begin with the standard imports. Motivating random forests. Decision trees. Random forests are an example of an ensemble learner built on decision trees. For this reason, we'll start by discussing decision trees themselves. Decision trees are extremely intuitive ways to classify or label objects. You simply ask a series of questions designed to zero in on the classification. Let's now look at an example of this. Creating a decision tree. Consider the following two-dimensional data, which has one of 4 class labels. A simple decision tree built on this data will iteratively split the data along one or the other axis according to some quantitative criterion, and at each level, assign the label of the new region according to a majority vote of points within it. This process of fitting a decision tree to our data can be done in Scikit-Learn with the decision tree classifier estimator. Let's write a quick utility function to help us visualize the output of the classifier. Now we can examine what the decision tree classification looks like. Notice that as the depth increases, we tend to get very strangely shaped classification regions. For example, at a depth of 5, there is a tall and skinny purple region between the yellow and blue regions. That is, this decision tree, even at only 5 levels deep, is clearly overfitting our data. Decision trees and overfitting. Such overfitting turns out to be a general property of decision trees. It is very easy to go too deep in the tree, and thus to fit details of the particular data, rather than the overall properties of the distributions they are drawn from. Ensembles of estimators, random forests. This notion that multiple overfitting estimators can be combined to reduce the effect of this overfitting is what underlies an ensemble method called bagging. This type of bagging classification can be done manually using Scikit-Learn's bagging classifier meta-estimator, as shown here. In this example, we have randomized the data by fitting each estimator with a random subset of 80% of the training points. In Scikit-Learn, such an optimized ensemble of randomized decision trees is implemented in the random forest classifier estimator, which takes care of all the randomization automatically. We see that by averaging over 100 randomly perturbed models, we end up with an overall model that is much closer to our intuition about how the parameter space should be split. Random forest regression. In the previous section, we considered random forests within the context of classification. Random forests can also be made to work in the case of regression. The estimator to use for this is the random forest regressor, and the syntax is very similar to what we saw earlier. Consider the following data, drawn from the combination of a fast and slow oscillation. Using the random forest regressor, we can find the best fit curve as follows. Here the true model is shown in the smooth gray curve, while the random forest model is shown by the jagged red curve. As you can see, the non-parametric random forest model is flexible enough to fit the multi-period data, without us needing to specifying a multi-period model. Example, random forest for classifying digits. Let's use that again here to see how the random forest classifier can be used in this context. To remind us what we're looking at, we'll visualize the first few data points. We can quickly classify the digits using a random forest as follows. We can take a look at the classification report for this classifier. And for good measure, plot the confusion matrix. We find that a simple, untuned random forest results in a very accurate classification of the digits data. Principal component analysis. Up until now, we have been looking in depth at supervised learning estimators, those estimators that predict labels based on labeled training data. Here we begin looking at several unsupervised estimators, which can highlight interesting aspects of the data without reference to any known labels. In this section, we explore what is perhaps one of the most broadly used of unsupervised algorithms, principal component analysis (PCA). We begin with the standard imports. Introducing principal component analysis. Principal component analysis is a fast and flexible unsupervised method for dimensionality reduction in data. Its behavior is easiest to visualize by looking at a two-dimensional dataset. Consider the following 200 points. By I, it is clear that there is a nearly linear relationship between the x and y variables. This is reminiscent of the linear regression data we explored in depth. Linear, but the problem setting here is slightly different. Rather than attempting to predict the y values from the x values, the unsupervised learning problem attempts to learn about the relationship between the x and y values. In principal component analysis, this relationship is quantified by finding a list of the principal axes in the data and using those axes to describe the dataset. Using Scikit-Learn's PCA estimator, we can compute this as follows. The fit learns some quantities from the data, most importantly the components, and explain variance. To see what these numbers mean, let's visualize them as vectors over the input data, using the components to define the direction of the vector and the explain variance to define the squared length of the vector. These vectors represent the principal axis of the data, and the length of the vector is an indication of how important that axis is in describing the distribution of the data more precisely. It is a measure of the variance of the data when projected onto that axis. PCA is dimensionality reduction. Using PCA for dimensionality reduction, involves zeroing out one or more of the smallest principal components, resulting in a lower dimensional projection of the data that preserves the maximal data variance. Here is an example of using PCA as a dimensionality reduction transform. The transformed data has been reduced to a single dimension. To understand the effect of this dimensionality reduction, we can perform the inverse transform of this reduced data and plot it along with the original data. The light points are the original data, while the dark points are the projected version. PCA for visualization, handwritten digits. The usefulness of the dimensionality reduction may not be entirely apparent in only 2 dimensions, but becomes much more clear when looking at high-dimensional data. We start by loading the data. Recall that the data consists of 8 × 8 pixel images, meaning that they are 64-dimensional. We can now plot the first 2 principal components of each point to learn about the data. Recall what these components mean. The full data is a 64-dimensional point cloud, and these points are the projection of each data point along the directions with the largest variance. Choosing the number of components. A vital part of using PCA in practice is the ability to estimate how many components are needed to describe the data. This can be determined by looking at the cumulative explained variance ratio as a function of the number of components. This curve quantifies how much of the total 64-dimensional variance is contained within the first 8 components. PCA is noise filtering. PCA can also be used as a filtering approach for noisy data. Let's see how this looks with the digits data. First, we will plot several of the input noise-free data. Now let's add some random noise to create a noisy dataset and replot it. It's clear by eye that the images are noisy and contain spurious pixels. Let's train a PCA on the noisy data, requesting that the projection preserve 50% of the variance. Here 50% of the variance amounts to 12 principal components. Now we compute these components and then use the inverse of the transform to reconstruct the filtered digits. Example: Eigenfaces. Earlier we explored an example of using a PCA projection as a feature selector for facial recognition with a support vector machines. Recall that we were using the labeled faces in the wild dataset made available through Scikit-Learn. Let's take a look at the principal axes that span this dataset. We will take a look at the first 150 components. In this case, it can be interesting to visualize the images associated with the first several principal components. The results are very interesting and give us insight into how the images vary. For example, the first few eigenfaces from the top left seem to be associated with the angle of lighting on the face, and later principal vectors seem to be picking out certain features, such as eyes, noses, and lips. Let's take a look at the cumulative variance of these components to see how much of the data information the projection is preserving. We see that these 150 components account for just over 90% of the variance. To make this more concrete, we can compare the input images with the images reconstructed from these 150 components. The top row here shows the input images, while the bottom row shows the reconstruction of the images from just 150 of the 3,000 initial features. Manifold learning. We have seen how principal component analysis (PCA) can be used in the dimensionality reduction task, reducing the number of features of a dataset while maintaining the essential relationships between the points. Here we will demonstrate a number of manifold methods, going most deeply into a couple techniques: multidimensional scaling, MDS, locally linear embedding, LLE, and isometric mapping, Isomap. We begin with the standard imports. Manifold learning. To make these concepts more clear, let's start by generating some two-dimensional data that we can use to define a manifold. Here is a function that will create data in the shape of the word hello. Let's call the function and visualize the resulting data. The output is two-dimensional and consists of points drawn in the shape of the word hello. This data form will help us to see visually what these algorithms are doing. Multidimensional scaling. Looking at data like this, we can see that the particular choice of x and y values of the dataset are not the most fundamental description of the data. We can scale, shrink, or rotate the data, and the hello will still be apparent. For example, if we use a rotation matrix to rotate the data, the x and y values change, but the data is still fundamentally the same. This tells us that the x and y values are not necessarily fundamental to the relationships in the data. Let's use Scikit-Learn's efficient pairwise distances function to do this for our original data. As promised, for our n equals 1000 points, we obtain a 1000 times 1000 matrix, which can be visualized as shown here. If we similarly construct a distance matrix for our rotated and translated data, we see that it is the same. This distance matrix gives us a representation of our data that is invariant to rotations and translations, but the visualization of the matrix above is not entirely intuitive. Let's see how it works for our distance matrix, using the pre-computed dissimilarity to specify that we are passing a distance matrix. The MDS algorithm recovers one of the possible two-dimensional coordinate representations of our data, using only the A times A distance matrix, describing the relationship between the data points. MDS is manifold learning. The usefulness of this becomes more apparent when we consider the fact that distance matrices can be computed from data in any dimension. Let's visualize these points to see what we're working with. We can now ask the MDS estimator to input this three-dimensional data, compute the distance matrix, and then determine the optimal two-dimensional embedding for this distance matrix. The result recovers a representation of the original data. In the case of MDS, the quantity preserved is the distance between every pair of points. Nonlinear embeddings, where MDS fails. Our discussion thus far has considered linear embeddings, which essentially consist of rotations, translations, and scalings of data into higher dimensional spaces. Consider the following embedding, which takes the input and contorts it into an S shape in 3 dimensions. This is again 3-dimensional data, but we can see that the embedding is much more complicated. The fundamental relationships between the data points are still there, but this time the data has been transformed in a nonlinear way. It has been wrapped up into the shape of an S. If we try a simple MDS algorithm on this data, it is not able to unwrap this nonlinear embedding, and we lose track of the fundamental relationships in the embedded manifold. The best two-dimensional linear embedding does not unwrap the S-curve, but instead throws out the original Y-axis. Nonlinear manifolds, locally linear embedding. How can we move forward here? Stepping back, we can see that the source of the problem is that MDS tries to preserve distances between faraway points when constructing the embedding. LLE comes in a number of flavors. Here we will use the modified LLE algorithm to recover the embedded two-dimensional manifold. In general, modified LLE does better than other flavors of the algorithm at recovering well-defined manifolds with very little distortion. The result remains somewhat distorted compared to our original manifold, but captures the essential relationships in the data. Example, Isomap on faces. One place manifold learning is often used is in understanding the relationship between high-dimensional data points. Running this command will download the data and cache it in your home directory for later use. We have 2,370 images, each with 2,914 pixels. In other words, the images can be thought of as data points in a 2,914 dimensional space. Let's quickly visualize several of these images to see what we're working with. We would like to plot a low-dimensional embedding of the 2914 dimensional data to learn the fundamental relationships between the images. We see that for this data, nearly 100 components are required to preserve 90% of the variance. This tells us that the data is intrinsically very high dimensional. It can't be described linearly with just a few components. We can compute an Isomap embedding on these faces using the same pattern shown before. The output is a two-dimensional projection of all the input images. To get a better idea of what the projection tells us, let's define a function that will output image thumbnails at the locations of the projections. Calling this function now, we see the result. The result is interesting. The first two Isomap dimensions seem to describe global image features, the overall darkness or lightness of the image from left to right, and the general orientation of the face from bottom to top. K-means clustering. We will move on to another class of unsupervised machine learning models, clustering algorithms. Clustering algorithms seek to learn from the properties of the data an optimal division or discrete labeling of groups of points. We begin with the standard imports. Introducing K-means. The K-means algorithm searches for a predetermined number of clusters within an unlabeled multidimensional dataset. It accomplishes this using a simple conception of what the optimal clustering looks like. The cluster center is the arithmetic mean of all the points belonging to the cluster. Each point is closer to its own cluster center than to other cluster centers. To emphasize that this is an unsupervised algorithm, we will leave the labels out of the visualization. By I, it is relatively easy to pick out the four clusters. The K-means algorithm does this automatically, and Scikit-Learn uses the typical estimator API. Let's visualize the results by plotting the data colored by these labels. We will also plot the cluster centers as determined by the K-means estimator. K-means algorithm, expectation maximization. The K-means algorithm is simple enough that we can write it in a few lines of code. The following is a very basic implementation. Most well-tested implementations will do a bit more than this under the hood, but the preceding function gives the gist of the expectation maximization approach. The globally optimal result may not be achieved. For example, if we use a different random seed in our simple procedure, the particular starting guesses lead to poor results. The number of clusters must be selected beforehand. Another common challenge with K-means is that you must tell it how many clusters you expect. It cannot learn the number of clusters from the data. For example, if we ask the algorithm to identify 6 clusters, it will happily proceed and find the best 6 clusters. K-means is limited to linear cluster boundaries. The fundamental model assumptions of K-means, points will be closer to their own cluster center than to others, means that the algorithm will often be ineffective if the clusters have complicated geometries. Consider the following data, along with the cluster labels found by the typical K-means approach. One version of this kernelized K-means is implemented in Scikit-Learn within the spectral clustering estimator. It uses the graph of nearest neighbors to compute a higher dimensional representation of the data, and then assigns labels using a K-means algorithm. We see that with this kernel transform approach, the kernelized K-means is able to find the more complicated nonlinear boundaries between clusters. We see that with this kernel transform approach, the kernelized K-means is able to find the more complicated nonlinear boundaries between clusters. Example 1, K-means on digits. Here we will attempt to use K-means to try to identify similar digits without using the original label information. This might be similar to a first step in extracting meaning from a new dataset, about which you don't have any a priori label information. The clustering can be performed as we did before. The result is 10 clusters in 64 dimensions. Notice that the cluster centers themselves are 64 dimensional points and can themselves be interpreted as the typical digit within the cluster. Let's see what these cluster centers look like. We see that even without the labels, k-means is able to find clusters whose centers are recognizable digits, with perhaps the exception of 1 and 8. Because k-means knows nothing about the identity of the cluster, the 0-9 labels may be permuted. We can fix this by matching each learn cluster label with the true labels found in them. Now we can check how accurate our unsupervised clustering was in finding similar digits within the data. With just a simple k-means algorithm, we discovered the correct grouping for 80% of the input digits. Let's check the confusion matrix for this. As we might expect from the cluster centers we visualized before, the main point of confusion is between the 8s and 1s. TSNE is a nonlinear embedding algorithm that is particularly adept at preserving points within clusters. Let's see how it does. That's nearly 92% classification accuracy without using the labels. Example 2. K-means for color compression. One interesting application of clustering is in color compression within images. For example, consider the image shown in the following figure, which is from the Scikit-Learn datasets module. For this to work, you'll have to have the PyPython package installed. The image itself is stored in a three-dimensional array of size, height, width, RGB, containing red, blue, green contributions as integers from 0 to 255. One way we can view this set of pixels is as a cloud of points in a three-dimensional color space. We will reshape the data to Ensembles x n features and rescale the colors so that they lie between 0 and 1. We can visualize these pixels in this color space using a subset of 10,000 pixels for efficiency. Now let's reduce these 16 million colors to just 16 colors using a k-means clustering across the pixel space. The result is a recoloring of the original pixels, where each pixel is assigned the color of its closest cluster center. Plotting these new colors in the image space rather than the pixel space shows us the effect of this. Some detail is certainly lost in the rightmost panel, but the overall image is still easily recognizable. Gaussian mixture models. In this section we will take a look at Gaussian mixture models, GMMs, which can be viewed as an extension of the ideas behind k-means, but can also be a powerful tool for estimation, beyond simple clustering. We begin with the standard imports. Motivating GMM, weaknesses of k-means. Let's take a look at some of the weaknesses of k-means and think about how we might improve the cluster model. For example, if we have simple blobs of data, the k-means algorithm can quickly label those clusters in a way that closely matches what we might do by eye. This radius acts as a hard cutoff for cluster assignment within the training set. Any point outside this circle is not considered a member of the cluster. We can visualize this cluster model with the following function. An important observation for k-means is that these cluster models must be circular. K-means has no built-in way of accounting for oblong or elliptical clusters. So, for example, if we take the same data and transform it, the cluster assignments end up becoming muddled. By eye, we recognize that these transformed clusters are non-circular, and thus circular clusters would be a poor fit. Generalizing Gaussian mixture models. A Gaussian mixture model, GMM, attempts to find a mixture of multi-dimensional Gaussian probability distributions that best model any input dataset. In the simplest case, GMMs can be used for finding clusters in the same manner as k-means. But because GMM contains a probabilistic model under the hood, It is also possible to find probabilistic cluster assignments in Scikit-Learn. This is done using the predict-proba method. This returns a matrix of size n samples, n clusters, which measures the probability that any point belongs to the given cluster. We can visualize this uncertainty by, for example, making the size of each point proportional to the certainty of its prediction. Looking at the following figure, we can see that it is precisely the points at the boundaries between clusters that reflect this uncertainty of cluster assignment. Let's create a function that will help us visualize the locations and shapes of the GMM clusters by drawing ellipses based on the GMM output. With this in place, we can take a look at what the 4-component GMM gives us for our initial data. Similarly, we can use the GMM approach to fit our stretch dataset, allowing for a full covariance. The model will fit even very oblong, stretched out clusters. This makes clear that GMM addresses the two main practical issues with k-means encountered before. GMM is density estimation. Though GMM is often categorized as a clustering algorithm, fundamentally it is an algorithm for density estimation. As an example, consider some data generated from Scikit-Learn's MakeMoons function, which we saw in k-means clustering. If we try to fit this with a 2-component GMM, viewed as a clustering model, the results are not particularly useful. But if we instead use many more components and ignore the cluster labels, we find a fit that is much closer to the input data. Here the mixture of 16 Gaussians serves not to find separated clusters of data, but rather to model the overall distribution of the input data. How many components? Let's look at the AIC and BIC as a function as the number of GMM components for our Moon dataset. The optimal number of clusters is the value that minimizes the AIC or BIC depending on which approximation we wish to use. Example, GMM for generating new data. Here we will run with this idea and generate new handwritten digits from the standard digits corpus that we have used before. To start with, let's load the digits data using Scikit-Learn's data tools. Next, let's plot the first 100 of these to recall exactly what we're looking at. We have nearly 1,800 digits in 64 dimensions, and we can build a GMM on top of these to generate more. Here we will use a straightforward PCA, asking it to preserve 99% of the variance in the projected data. The result is 41 dimensions, a reduction of nearly 1/3 with almost no information loss. Given this projected data, let's use the AIC to get a gauge for the number of GMM components we should use. It appears that around 110 components minimizes the AIC. We will use this model. Let's quickly fit this to the data and confirm that it is converged. Kernel density estimation. Kernel density estimation, KDE, is in some senses an algorithm which takes the mixture of Gaussian's idea to its logical extreme. It uses a mixture consisting of one Gaussian component per point, resulting in an essentially non-parametric estimator of density. In this section, we will explore the motivation and uses of KDE. We begin with the standard imports. Motivating KDE. Histograms. As already discussed, a density estimator is an algorithm which seeks to model the probability distribution that generated a dataset. For example, let's create some data that is drawn from two normal distributions. We have previously seen that the standard count-based histogram can be created with the plt.hist function. By specifying the norm parameter of the histogram, we end up with a normalized histogram where the height of the bins does not reflect counts, but instead reflects probability density. Notice that for equal binning, this normalization simply changes the scale on the y-axis, leaving the relative heights essentially the same as in a histogram built from counts. This normalization is chosen so that the total area under the histogram is equal to 1, as we can confirm by looking at the output of the histogram function. One of the issues with using a histogram as a density estimator is that the choice of bin size and location can lead to representations that have qualitatively different features. For example, if we look at a version of this data with only 20 points, the choice of how to draw the bins can lead to an entirely different interpretation of the data. Consider this example. On the left, the histogram makes clear that this is a bimodal distribution. Stepping back, we can think of a histogram as a stack of blocks, where we stack one block within each bin on top of each point in the dataset. Let's view this directly. The problem with our two binnings stems from the fact that the height of the block stack often reflects not on the actual density of points nearby, but on coincidences of how the bins align with the data points. If we do this, the blocks won't be aligned, but we can add their contributions at each location along the x-axis to find the result. Let's try this. The result looks a bit messy, but is a much more robust reflection of the actual data characteristics than is the standard histogram. Let's use a standard normal curve at each point instead of a block. This smoothed-out plot with a Gaussian distribution contributed at the location of each input point gives a much more accurate idea of the shape of the data distribution, and one which has much less variance. Kernel density estimation in practice. The kernel bandwidth, which is a free parameter, can be determined using Scikit-Learn standard cross-validation tools, as we will soon see. Let's first show a simple example of replicating the above plot using the Scikit-Learn kernel density estimator. The result here is normalized such that the area under the curve is equal to 1. Selecting the bandwidth via cross-validation. Because we are looking at such a small dataset, we will use leave one out cross-validation, which minimizes the reduction in training set size for each cross-validation trial. Now we can find the choice of bandwidth which maximizes the score, which in this case defaults to the log likelihood. The optimal bandwidth happens to be very close to what we used in the example plot earlier, where the bandwidth was 1.0. Application: a face detection. This chapter has explored a number of the central concepts and algorithms of machine learning. We will develop a simple face detection pipeline using machine learning algorithms and concepts we've seen. We begin with the standard imports. HOG Features. The histogram of gradients is a straightforward feature extraction procedure that was developed in the context of identifying pedestrians within images. A fast HOG extractor is built into the Scikit image project, and we can try it out relatively quickly and visualize the oriented gradients within each cell. This gives us a sample of 13,000 face images to use for training. Find faces in a new image. Now that we have this model in place, let's grab a new image and see how the model does. Next, let's create a window that iterates over patches of this image and compute HOG features for each patch. Finally, we can take these featured patches and use our model to evaluate whether each patch contains a face. I will appreciate it if you subscribe and like the video. Thanks for watching.